Hello and welcome everyone. So I'll be explaining educational code forces round 122, problem D named make them equal. So before jumping on to the solution, I just want to say that in order to do this problem, you need to know what is dynamic programming, and especially in order to solve this problem, you need to know how the basic knapsack classic, or so-called classic knapsack DP problem works, or you need to know how the solution works, because this problem is like you could say a variation of that with a slight bit of modifications, but at the end of the day it's actually we could relate this problem to typical classic knapsack problem. I'll show you how we're going to do that, but yeah, let's jump on to the statement. First of all, what you're given is you're going to be given an array. Like, you will assume that you have an array of n integers, and each and every element initially will be 1. Okay, and you're gonna input n and k for each and every test case, and you're gonna input 2 arrays also, so there will be a total of 3 arrays and an integer k. Those 3 arrays are like, first of all, I could tell that one of the arrays is A, and containing all the numbers equal, all the elements equal to 1, and we have another array B. Now that's going to contain some values inside of it, and their constraints are going to be like from 1 till 10 to the power 3, and another array C. Basically, C is actually coin, or you could say in a knapsack, classic knapsack fashion, you could call this coin array as a profit array. They both act as the same. You're gonna convert, when you're gonna convert it to code, you're gonna act this array, like C, or like the coins array, acts the same as the profit when we solve knapsack problem, typical knapsack problem. Okay, yeah. So basically what we're gonna have to do is we're gonna have to find out the maximum number of coins that you can get. Meaning, I could also say that what is the maximum number of profit if I like relate the coins array to the profit array. So like the maximum number of coins that you can get by performing no more than k operations. So here k is actually referring to each and every operations, or at most how many operations I can make to array A, such that I could and I use these particular indexes C coins, such that I could maximize the number of coins. But you need to know that yeah, first of all, yeah, we have the operations will be like at most k operations, and also in a typical knapsack fashion, I could say that this k here, and we could relate this k and this array bi as our weight transition in a typical knapsack. I'll show you how it's being done. Now, what are the operations that we could perform inside our array A, which is consisting of all the numbers equal to 1? That operation is quite interesting. It's they're saying that it's going to be AI equal to AI plus AI divided by X. Now this X can be any number greater than 0, and any number greater than 0. But if you notice that, okay, now what will be the value that actually going to make sense when we input in each and every k operations, I mean up till k, which values of X are actually going to matter for each and every AI? Let's say that AI initially was 1, but we made some operations, and in between, let's assume that AI is 5. Now, if AI is 5, let's assume that AI was 5. Now if we're gonna make an operation to 5, which are the values of x that's gonna actually make sense that we could move forward? It's actually always gonna be from 1 till 5, meaning for each and every I, if I wanna find out how many for each and every I of AI like this, if I want to make an operations to this in order to increase my, at the end of the day, my goal would be to increase AI. Why is that? Because if I want to make this arrays like if I want to increase the maximum number of coins, what I need to do is I need to, and if I want to pick that particular index with having a bit of a coins on that particular index, I need to make AI equal to BI. Now the question is, BI can have any values, and my initial task would be to make each and my initial task would be to, like, if I want to take this index containing this number of, let's say any number, let's say y number of coins, then I need to make this one equal to initially need to 1 equal to the value that is corresponding or referring to that particular same index but in a different array, which is called B. I hope you I tried to make you understand. I hope you do understand what I'm trying to say here. I'm trying to make a point here, which is, like, for each and every index, if I want to pick that index as in order to increase my maximum number of coins, meaning that I'm going to take that particular index's coins, if I want to make that, I have to make this value, which is inside A, equal to B. Now the only way that I could do that is by following an operations, which is this, meaning AI should be equal to AI plus AI divided by X. Now as I told you before, what could be the convenient values that we could perform such that this AI would increase and become some value of that particular index's some value of BI. That X that X's particular operations would always be from 1 till I, because further values would make this part bigger, this X bigger. Imagine if X was greater than AI, what would happen? It would result nothing, because it's a floor value. First of all, we're dividing that, so at the end of the day it's gonna give me 0, which means X should be from 1 till I. So that was the point here. Now the first and foremost observation is that we're gonna like, in order to get to the solution, first of all we have to do something here, which is, I'm gonna assume that, like, I don't actually necessarily know which way to go, which indexes to pick, because, like, it's a there's no actually particular greedy solution to this problem. I cannot claim any index that I can make, because, like, there's, like, each and every operation takes each and every value from K, and it's actually gonna matter a bit, and that's why what we're gonna try to do here is that we're gonna assume that, what if I take this index? What if I take this index? What if I take this index? So on and so forth, including each and every value of A. What we're gonna try to do is, for each and every value of A, we're gonna make this one equal to B of I, and we're gonna try to find out that how many operations did I have to use in order to make from 1 till BI. That BI could be anything. It could be 5, it could be 3, it could be up to 10 to the power 3. So for each and every, now I cannot just run through a loop and make those values equal. That's going to take a whole lot of time. But there's a clue, which is okay, so, like, what we're gonna have to do is, for each and every index, that one needs to be equal to that particular bi, and we need to find out how many operations did it took. Because at the end of the day, these operations do make sense, because they if I could somehow find out, in order to make this particular value equal to this, how many operations did I need to use, I could put and store those values inside another array, which is going to be a weight array. Yes, that would definitely lead us to our classical knapsack weight. Classical knapsack weight, because the operations are working correspondingly to the weight, if I compare it with the classical knapsack. Now, the main thing is that how are we going to find out for each and every index that thing? Now, first of all, initially each and every value will be 1, right? We could do something like that. We could, even before taking the test cases, we could do something like this. We're gonna, this part would also, we could consider it as a dynamic way, or like dynamic programming way, because what we're gonna be doing, it's actually like an init function, you could say, without taking, even before taking the test cases, we're considering this part, because we need to find out that. Now, what I'm gonna do, from 1 till 10 to the power 3, I will try to say, whenever in any dynamic programming problem, always try to think in the middle process, not the start, not the end, but in the middle process. And you will start from the middle, and you will think about it, what's gonna happen now. Now, normally what happens, let's say we have one index of 1, we make some operations and we make some value, let's say y, and then from that y we make some operations, let's say that particular bi comes up, right? Now, how many operations did we have to make here? Only 2 operations, right? So that's exactly the point I'm trying to make. We're gonna assume that we have somehow managed to get here, which is in the middle process. We're not getting there, but we're quite getting there, but not in our final destinations. We're in the middle process. Now, what's gonna happen in the middle process? First of all, this guy here, he knows how he got here from 1, right? That's it. He knows how he got from 1, because I have that track, that how many operations did I took from 1 till this. Now, from this, if I want to go forward, how many possible ways that I can go forward for this particular value? Let's say this is w. How many particular way? Exactly, the operation that we have to choose x. How are we going to choose x? From 1 till w, because I said that for every particular I'm going to assume that I'm going to assume that if I want to take x, that the only values of x that's going to be convenient in order to go forward or move forward, it's going to be 1 till ai, because they eventually increases the possibility to move forward. And yeah, that's exactly what we're gonna do. So yeah, we were in the middle process. We know that we got somehow this value from 1 till this, and we know how many operations we took. Now, if I want to move forward, what am I gonna have to do? I'm gonna have to add only 1, because I'm making a move. Because if I make a move, if I make an operations from here, that would be w plus w divided by x, and that x would be possible values from 1 till w. And finally, this value here, if I assign it to as y, let's say p, what's gonna happen to that p? if it moves, so like I'm making an operation and I found some integer p. Now can I say something like that this p actually came through w? One of the possible ways that this p came is through w. Now how did w came through? It came through 1. So eventually p comes, one of the possible ways that p could be available to us is from 1 till w and then w till p. I hope you're getting that. One from 1 till w, from w till p. Now there could be many other ways that we could come up to this p, so we have to track the minimum distance out of it. I hope you're getting that. So ultimately it's going to be like the minimum distance of what was before and what is now that we are calculating, which is the minimum distance of this plus 1 comma of minimum distance that we got earlier for this integer. So that's how we're gonna actually calculate that. I'll show you in the code. I'll show you the code in the description though. Yeah, that was the fun part, and that's how we're gonna get the weight array, so-called. And if I could somehow find the weight array, and if I do have the, and I've already told you that I have the coin array, I have the weight, I'm gonna make this as my weight array, new weight array, and I have, now what's gonna be the total bag of weight? That's gonna be the sum of all these weights, or I'm actually assuming that I'm gonna use all of it, which eventually actually might not happen to. I'm gonna sum all of these operations, and I'm gonna say that okay, total number of operations if I use all of these n integers is gonna be sum or whatever it is, and I'm gonna compare with k, because this could be greater than k, this could be less than k. And surprisingly, if you analyze a bit, this sum value, the sum of all the operations that we took, it's not more than n times 12. Which means, as you can see, k's constraint is up to 10 to the power 6. So in a conventional way, if I would do the knapsack, classical knapsack, it might give us time limit exceeded, or memory limit exceeded too, I guess. Might give memory limit or time limit too. So that won't happen, because the sum of these operations of the n integers, it could be highest, it could go to n times 12. So that is actually within the range of 10 to the power 3, more or less. So then what we're gonna have to do is like this conventional, easy, conventional classical knapsack. It's the same as the same code. It's like absolutely same, just you're gonna like find out what's gonna be the maximum number of coins instead of the maximum number of profits. So it's gonna work as the profit, and for the array B, it's gonna you could measure it as how many weights we got, meaning the operations that we needed in order to make AI equal to BI, and check whether I can take or not take whatever it is. I hope you see the knapsack. If you don't know how to do it, it's available on the internet, and let's take you to the code part. You'll understand more how you're gonna do that after that. So like there's gonna be a pre-compute before taking the test case T. There you go. And there was the fun part. Oh, one thing to say is that what's gonna be the base case? The base case is that for 1, let's say I want to make 1 from 1 to 1. Now you tell me, if I want to make 1 to 1, obviously it's going to give me, it's going to take the 0 number of operations. That's obvious. As you can see, it's pretty obvious. From 1 to 1, it's just gonna take 0 number of operations. So yeah, that was the base case, and making that basic base case, we're moving forward, and that's the part that I was describing earlier. I'm gonna take the minimum values when we're like discussing here. I hope you get that. That's just you can implement it easily. It's not that hard. And after that, we're just making everything my weight. Okay, the weight array, and this is the profit, and this minimum part is like it could be, the sum could be less than k. If it's greater than k, then the sum will be sum, or it's still, if it's like this was the part where I was talking about that sum could be at most n times 12. That's why we're taking this minimum. We're not considering taking k's value up to 10 to the power 6, because that might not get accepted. And after that, that's just the dynamic classical knapsack dynamic precomputation of -1, making it every 2D of the 2D DP array. And this is the final solve function, which is doing the basic knapsack operation. If whether or not I'm gonna make that decision, I'm gonna take that index or not. Based on that, I'm making my move, making my decisions. And if I take a particular index, I'm gonna add that profit, or so-called coins, and out of I might not take that coin. So there are like two possible ways that I could do that, and out of those possible ways, I'm gonna take the maximum one and put that inside the DP of I of sum. And this was the it's pretty easy if you just know how to do classical knapsack. This part is really relatable to that problem, that classical problem. So I hope I made you understand. Please don't forget to like, subscribe, and share, and it means a lot. And yeah, till next time, goodbye.